CodeUp Live. I'm Mansa. I'm a part of the marketing team here at PayU. CodeUp Live is a series that PayU runs. It's for developers to talk to subject matter experts about various topics. So I think this is one of the CodeUp Lives that we have not done a CodeUp Live in a long time, and we have just thought that there's no one better to bring in as a part of this conversation other than someone from PayU itself. I'm very sorry. I see a lag in my video, but I hope you all are able to hear me and see me clearly. Venkat, if you can just confirm that, please.
Yeah, your audio and video both are in sync.
Yes, yes. Thank you so much, everyone, for being a part of this. Thank you for coming here and conversing. Thank you, Venkat, for coming here and conversing with us about a topic that we know is important to developers. So here today, our subject matter expert from PayU itself, we have Venkat. He's a part of the engineering team at PayU, and he's a senior technical architect. So there's no better person to talk about data structures to you than Venkat here. So Venkat, before we go into the topic, would you like to just talk about yourself and then we can go on to your presentation?
Yeah, sure. And thanks, Manasa. Yeah, hi. I am Venkateswamy Pavale, and I am working as a senior technical architect in the payments department. I can say software development department in the PayU, where I am taking care of the technological architecture and its proper implementation. Yeah, it is the very high level summary about what I am and what I am doing here. And today I am going to present, basically explain about the data structures. So data structures is a part of everyday life for us. Uh, Not only data structure, if you are trying to implement something and you are writing some piece of code, you have to be conscious about that piece of code what you are writing, that should be performant. Otherwise it will lead into the lot of performance complications. Might be at the starting or the very first deployment of your code you might not feel, but once the data grows and lot of traffic is coming up, then you can feel that pain, and it will lead into a lot of maintenance issues. Yeah, instead of you concentrating on your innovative product development, now you should be strict to solving all of these problems. So it is very useful to know about the data structures and the complexities and apply those ones in your real time um, code whatever you are writing. Yeah, so this is very just a brief intro and the pitching point for this data structures presentation. Yeah, so right. So the data structure, I think most of the guys, whoever is working in the software industry, might came from the computer science background, and it might be a subject in their first or second year of their academic career. I think so, and might be while we are working on our regular projects, it is obvious that we will actually lose our knowledge about those things. But based upon the changing world and based upon the competition right now we have in the industry, we have to know, and this is required. Yeah, so I am just starting from the basics. Yeah, like what are data
Venkat, before we go in, just a note to all of our viewers here, in case you have any questions for Venkat, be it topic related and otherwise also, if Venkat has the answer to it, he'll be able to help you out with it. In case there is anything that you feel is unanswered, you can always reach out to him on LinkedIn. He's available there. And yes, thank you so much again for being here. Over to you, Venkat. Very sorry for the
Yeah, thanks.
interruption.
Nice. Right. So first we need to know what is data structure. Yeah. So what is data structure? It is just like a simple word. Yeah. And what is data structure is, so the data structure is something that programmatically we can store the data and use in a efficient way. Okay, so today all we are working is on the information systems, even though we are calling those ones as a software applications. And the information or the data is the key for the information systems, and data flow makes all of these applications working. Means the data structures is the programmatic way of storing that data and efficiently using it. And it has couple of things. So one is it has the contract, which we will call as interface. Each and every data set can have a couple of operations, I can say. That a set of operations we can call as a interface. And its implementation, so the implementation can be programming language specific, because the data structures can be implemented in the programming language what we chose to develop our application. Yeah. So, and if you see in most of the enterprise applications, uh, we are using these data structures, okay, in some way. Okay. So the data structures is everyday part of the life for everyone. Okay. uh, so that is what it is. Now that's okay, you just mentioned about the data structure, that's fine. But oh, sorry, due to some reason the
No
present.
problem. You can just share that again, Venkat. I'll just bring it up. No issues.
Yeah, not sure why it went off. Just a minute, please. Yeah. So now I a little bit touched upon why to learn the data structures. Yeah, as I mentioned, right, the data or the information is the key for all of our information systems, whatever we are developing to support our business capabilities for our organization. When the applications are getting complex and data is actually growing day by day, then wherever we wanted to do some sort of search to find out a piece of information in that entire data set, then the query what we are writing or the algorithm what we wrote, it might slow down. Initially not, but once the data grows, right? So let's consider that there might be some database or some inventory, whatever that type of the data store it is. We might have 1 million records in the system, as an example, right? So now I wanted to just search one item. How can I search? Either I need to just go through one by one from top to bottom, or it also depends upon the filter criteria what I am trying to put. So, to efficiently search or reduce the subsets of the data what I am searching here gives me performance of my application, right? For the piece of the code what I wrote. So, we have to use these data structures in the algorithms or the logic what we are writing to search the data, right? And
Venkat, would it be okay for you to answer a question right now, or do you want to do it at the end? Because we have a question.
okay, what I would prefer is that we can take the questions at the end.
Yes,
The
sure.
reason behind that one is that if we start taking the questions now, then we might need to skip couple of sections.
No,
If
Venkat, no problem. Yes, yes, we can pick that up later.
yeah, right. So now, right. Second one is the processor speed. Might be now we have the good processors which can do lot of computations per second. However, the data is also getting grow, right? If we are using a single core processor and we tested our algorithm up to that point, and now the data is getting grown, even the computation power we have, but still sometimes it can also be limit. Yeah, because the logic what we wrote is doing lot of calculations based upon the growing data. So we need to have an optimal algorithm over there, and optimal data structures needs to be used. Yeah. So if you take a couple of examples, like uh, if you have an application, right, and the data search whatever you are doing, that you are doing for a single query or single request, I can say. But when the concurrent requests or the multiple requests are coming, then those many instances of that query or the algorithm needs to spin up and needs to process. which will also slow down the performance of our algorithm what we wrote, right? So to handle all of these three types of scenarios in the situations, we need to use the proper optimized data structure and its the proper algorithms here. So that is why we need to learn data structures here. Yeah. So now that's okay. We talked about the data structures, but you mentioned it is data structures and algorithms. Then what is an algorithm? I think everyone knows. Algorithm is nothing but a series of steps or instructions which needs to be executed in sequential or in order so that we can get the desired output. Yeah, that is what algorithm is. Okay, so now that's okay, fine. What are the categories of algorithms we have in the context of the data structure? So, which is nothing but the categories are nothing but the type of operations what we are performing on the data structures. Just like an example, one is search, how efficiently we are going to search, and what is the optimum algorithm we are going to use for it. Sorting, on the data, right? And insert, update, and delete. These are the primary categories of algorithms in the context of the data structures what we have. Now, uh, since data structure is a kind of entity, it can have its own characteristics or the behaviors. So, what are those characteristics? So, one is all of the operations or the interface needs to be implemented correctly, and it should have the best time complexity, means it should use the cpu cycles efficiently so that it can handle the type of load what it is getting. Plus, even though we have the memory, nowadays we are getting that one in a cheaper cost, but still we can't avoid that. While you are writing an algorithm, might be you are defining some variables, or based upon the data might be some memory is getting allocated to into your ram. You have to write your logic in a such a way that it should use the memory as well in an optimum way. So that is called as space complexity. So we you have to properly utilize your memory, you have to properly utilize your cpu cycles, and the interfaces operations whatever you are going to implement, those should be in a correct way. So these are the characteristics what we have to follow while we are using the data structures. Now coming to the time complexity. So time complexity is called as execution time complexity as well. So what are the cases? How can we actually get to know that how can I derive the time complexity, and what are the different cases of the time complexity? Yeah, we can see that one here. So these are the ones. How worst your algorithm can perform, and what was the average case. Average case is nothing but it is in between the worst and best case, and the best case is the least time your algorithm is taking to perform an operation. So these are the three things I can get. I will touch these things going forward in the next slides. So now coming to the basic terminology. So if you see, as I mentioned, right, information or the data is key for information systems. So the data has certain terminology. We need to know that terminology so that we can efficiently communicate with our colleagues, or while we are discussing with regarding the any requirements or implementations there. So the first thing is that data is nothing but some sort of values or a set of value. Everything is a piece that is getting called as data, and a data item is a single unit of value. In that value might be an attribute. Okay, attributes value we can call as data. And group items, elementary items, these are the basic things what we know everything. So I'm just skipping that. These are the terminal: data item, group items, elementary items. Yeah. And attribute, entity set, field, record, file, all these are the basic terminology which is getting used in the data structures. Now We touched upon the algorithms, right? Similarly, the way we have the basic characteristics we need to follow for data structures, for algorithms as well, we need to follow a couple of characteristics so that we can efficiently implement the algorithms. So one is the algorithm, whatever you are trying to implement, that should be in a clear step by step way, and it should not have any conflict or unambiguous steps in it. And whatever the input you are taking, that needs to lead to a particular desired output. Yeah. And your algorithm might have a zero input or more as well. Let's take example of the sorting. A sorting algorithm might not take any input parameters, but it will just sort the data set. That's it. Yeah. So if you take something like insert or search kind of stuff, where you have to provide some input, the key or the data what you are willing to search, and output can be one or more, and that should be well defined. And your algorithm should have a finite number of steps, so that the algorithm can't keep on running infinite time, and your application will get hang up. Yeah, it should run a series of steps for certain type, and it should get out from there with your outcome. Yeah. So, and the algorithm should be feasible enough to use within your desired or within your the set of resources what you have. The resources are memory and computational resources, whatever you have. The algorithm should not instruct you saying that, hey, go and get me the large uh, large memory and also a high end processor. It should not. Algorithm should not derive those things. Yeah. And whatever the steps you are implementing, those should not be dependent on a programming language. Those are just like instructions. Based upon the programming language, you can just implement that's it. The algorithm should be defined in a such a way. So these are the characteristics what you need to follow while you are implementing an algorithm. Now, how to analyze the algorithm? What are the methodologies we have to analyze the algorithm? There are two things. One is before actually implementing your algorithm, you can also analyze it and came to know that what is my time complexity, what is my space complexity, which is the theoretical basis. Yeah. And once you implement it, then you can deploy that one on your particular server, and also analyze that how much memory and cpu it is taking, how much load it is able to actually uh, okay, how much load it is going to take handle. Yeah. So these are the things. So the first one is called as priori, which is a theoretical one. We are mostly going to concentrate on that particular analysis process. Second one is posteriori. It is not worth to go there because once you write the algorithm and you deploy it in one machine and test it, that's fine. So if you wanted to check for the worst case scenarios, then you have to have a uh, large memory and high end processors. So why should we go with that direction? So we, before implementing it, we should know about uh, the time complexity and space complexity of the algorithm what we are trying to implement, so that we can efficiently implement our application or a program. So these are the two types of analysis is what we are. Now, in this, whatever I am telling, right, the complexity, time and space, these are the two things what actually derive the efficiency of your algorithm. So these are the two important bits. And in nowadays, most of the developers or the architects uh, are not considering the space because we are getting the memory very cheaply. So they are only concentrating on the time complexities. Yeah. So if you and the time complexity is going to defined in a such a way that uh, each and every step whatever you are writing in your program or algorithm, it might be taking some amount of time. We are calling that one unit of time as an example. right? So you might have three steps uh, in your algorithm, and you are getting number of records, or the data set might be 100 or 200. So the time complexity is going to be multiplication of your the constant time whatever you derived for those three steps multiplied by the number of requests what it is processing, in simple terms. And the space complexity is you're going to derived in a such a way that while you are defining your algorithm, you can have two parts to it. Couple of things are fixed variables, a set of variables, and remaining are based upon your algorithm. The memory occupation might be keep on growing. Like example, if you are using the recursion, then for each and every recursion logic spin up, it is acquiring or occupying some space in the memory. The number of recursive calls it is going, the depth of the recursion what it is going to take, it will acquire that much of memory because it is going to in a stacked way, right? That is going to be little bit variant. So the space complexity is going to be calculated as the fixed memory what is required for your algorithm, and at the runtime how much your algorithm is going to occupy the memory. So in the combination of that, we can calculate the space complexity, and that can be actually calculated or derived based upon the steps or based upon the variables what you are defining in your algorithm. So let's go to the theoretical analysis, the priori analysis of the algorithms. So yeah, whatever the theoretical analysis we are going to do, these all are based upon some mathematical calculations. Okay, so if you take bubble sort as an example, what you are going to do, you are going to take two adjacent items and compare that. In that way you will keep on comparing that one for all of the items in it. Means you will just take the left side item and you will compare with all of the items, then you can go to the second item, you will compare all of the remaining items. Means you are running that loop in such a way that n into n minus 1 into n minus 2 into n minus 3 and so on up to 1. Means that expression is going to lead into the n into n minus 1 by 2, which is n square. Okay, so that is called as f of n square. Yeah, so means indirectly we are deriving some mathematical expression there based upon the algorithm steps what you defined. So ultimately that is what I am trying to say here is that in the theoretical analysis you are always going to use mathematical expressions to derive the time complexity here. So here, how can we derive time complexity? Is that as we discussed previously, we have best case complexity, average case complexity, and worst case complexity. Best case is nothing but the minimum time required to process a set of data, and average case is that it is between the minimum and maximum. Maximum is the worst case. If you are giving a high large number of data set to your algorithm, how much time it is going to take. So for the best case we are going to use the omega notation. For average case, theta notation. Worst case, big O notation. So if you might be based upon your experience, you might not had much about this omega notation and theta notation, because the best and average is not a concern for us. We have to actually target for the worst case. So hence the big O notation is popular. Okay, so whoever is talking about the algorithms or whoever is talking about the data structures, they will keep on talking with the big O notation. Yeah, these are the three things what we need to know. Now, what is omega notation? As I mentioned, omega notation is nothing but the best case, best optimized output what you are getting through your algorithm. So as I mentioned, it is just a lower bound, the best or minimum time it is taking. And if you see the expression here, the function notation omega of f on n is greater than equal to g of n. G of n is the function what you are deriving, and for a given constraint, which is greater than at 0, and a particular point which is called as n naught or some derived value. If you multiply that value with your number of steps what you defined, as I just explained about the bubble sort algorithm and its mathematical expressions, if you keep on varying that n, at some point it will be just greater than of that g of n, means which is the your lowest time consumption thing there. So that we are defining as a omega notation here. If you see in the graph, your actual f of n, actual function is going in this way. In the best case performance, up to the point of the n, which we are calling n not o is a k. Up to here, right? F of n is the best, but after that the g of n is the best. So this is the way how we are defining the mathematical expressions. However it is, I don't think people are going to just evaluate and find out that expressions based upon the number of steps what we have. At very high level they are calculating the functional expression or mathematical expression, and they are getting into, is it a o of 1, o of n, or o of log n, o of n log n, o of n square n3. In that it is based upon the number of loops or number of items you are derived. So no need to worry about these mathematical expressions. It is just to understand that how to calculate our time complexity, so that I can implement a best algorithm for my particular use case. In the big one notation, in the similar way. Okay, sorry, there was, yeah. So here the g of n is actually taking the more time than the f of n, right? So which is your worst case. Like example, in the bubble sort, as I mentioned, right? If the n is getting keep on increasing, if the n value is 1, right, then the number of comparisons what you can do is 2, means it will only utilize, let's consider that 2 cpu cycles, yeah, and your job is done. But if you are increasing the n, then the number of loops it is going to iterations it is going to take is more, means as compared to the f of n, where the n is a point, up to that the performance is okay. After that n, means the data is getting increased, then the performance will go down. Yeah. So we have to be careful there to define algorithm in such a way that your worst case time complexity is nearby your average. Okay, if you do that, at least you can say that your algorithm or the logic whatever you implemented, that is okay and it can handle any type of load. And theta notation, no need to worry about it. It is just a defining of the range between the minimum and maximum time complexities. That's it. And now going to the algorithms. What type of algorithms or what are the approaches we are going to implement in the algorithms while we are addressing a particular problem or the use case here? So there is a well-known term called as greedy algorithms. So greedy algorithms are nothing but finding out the nearest solution and just proceed further with that. In some cases it might not be helpful. Let's see what is that. And yeah, so it is designed, as I mentioned, that to just achieve the optimal solutions for a problem. And for the in the greedy algorithms, right, whatever the decisions we are going to take, that okay, this is the best fit of algorithm or the logic for this particular problem, it depends upon their domain model, means their functional area, in which functional area we are dealing with, and the applications what are targeting to that particular functional area. I will give you some example. And it might not be feasible if you wanted to use that one for some sort of big problem. Yeah. So let's take an examples here. Counting coins is an example. If you see, the problem statement here is that count 18 by using the coins 1, 2, 5, and 10. So As per the greedy principles, you have to just go and choose the nearest one or closest one. Means that you are going to choose 10 rupee coin as an example, right? Then how much is left? 8 rupees is left. And what is the nearest for the 8? The 5. Or you can consider that 5. Then how much is remaining? Free, right? So what is the nearest coin you have for the 3? 2. The remaining one is 1, so you can select 1. So if you see here, but just using 3 coins, you are able to count 18, right? If I change the coins 1 to 5, 1 to 5 and 10 to 1, 7 and 10, right? According to this greedy, it might end up having a lot of coins. So if you have a box, smaller box, those coins might not fit over there. Means you are defeating there for your purpose, right? If you wanted to calculate 15 by using 1, 7 and 10, according to the greedy, you are going to choose the nearest one, 10, right? And then what is the remaining after you choose 10? 5. What is the nearest one for the 5? Only 1, because 7 is greater than 5. So you are going to choose 5 1 rupee coins. Means you are ending up with the 6 coins. So these greedy algorithms are most popular in the network or in infra related problems addressing. Yeah. So this is one way to address the solution while defining the algorithms. The second type of algorithms are divide and conquer. So what it says is that take the big problem space and split it until you are getting a minute problem area, and start addressing those minute areas and just merge everything back so that you can find your solution. Okay. So where it can use different example, if you wanted to use the multi-threading or multitasking environment, you can apply this principle over there so that you can efficiently use your cpu or computational power. Yeah. So this is what greedy is. First, break down your problem statement into the smaller or smaller problems which can be independently solved. Solve it and merge it back. So examples of these algorithms are merge sort, quick sort, binary search, and these are the examples of these algorithms. Yeah. So let's take an example how we are going to do it. I have a small text or a string which has all of my small case letters. Now I wanted to make those ones as uppercase letters. How can I do? It is based upon the problem statement what you are addressing. You know that for each and every character, you wanted to just make that lowercase character to the uppercase. Means if you break down that entire string into the characters and start addressing one by one, right, and merge it up, then you are solved there. So this is how it is. So the problem area here, you break it down into multiple pieces like this, individual things a b c, in that way it came, and you are addressing each and every problem there, right, and converting into the upper cases. Finally you are summing up all of them, means concatenating it so that you are getting your desired outcome. So it is a simple thing, but I will explain going forward where we are using the divide and conquer and how we are using those ones uh, while we are doing a sorting kind of stuff. Now what is dynamic programming? Yeah. So if you see in the above use case, right, the letters, alphabets, they're used as unique a b c. There is no repeated character over there. So if you have repeated characters over there, addressing each and every character there might not be a feasible thing, right? Once you address or solve a particular problem, the problem for character a, then what you can do, no need to convert it into a, you can just get all of such type of instances over there and just replace or put your solution over there, right? So that is called as a dynamic programming here. So whatever the sub problems resultant we are getting, we are going to remember that. Remember means we are going to save that. If there is the same type of problem is coming, just we will apply the same outcome of the problem what we solved over there. Yeah. So that is called as dynamic programming in simple terms. So now coming to the data structures. Uh, Whatever we previously talked about, the data or the information which is key for our information systems, the data we are storing as a data sets. A data set is nothing but a collection of records, right? And a record we can consider as a data, and that collection we can consider as an array, right? So means we are dealing all of these things with the arrays itself. Okay, wherever you go and see, everything is in the arrays. So it is essential to understand first arrays and its operations in the data structures prior to going to the next data structure. Okay, so as I mentioned, right, array holds a collection of fixed number of data sets in it, and that array can be accessed via some index. Yeah, so and each and every container in the array, we can call that one as an element where actually we are storing the data. It can be a complex data object, or it can be a just elementary item like some value, exact value. Yeah, and as I mentioned, index is going to just to point each and every item what we have in the uh, array. How we are going to represent an array? We are going to represent an array in this way, right? Any of the programming language you can take, the syntax might be a little bit different. The type, you can mention that what type of data items you are going to store or hold in your array container, and what is the size of your array. Yeah, so and how the array is represented in memory, as an example, is that in this way you have all of those elements there, and you have the index which starts from 0 to 9. If you wanted to just get item 19, if you know the index, then you can just use that index directly. You can point to that and get that data out from there. Means even the number of items are getting increased in array. If you wanted to get an item with the index, it won't, the complexity is O of 1. Means either the number of items is 1 or 100, you are just doing a a single step execution to get that item out. Now, what are the operations we can perform on arrays? One is traverse, means we can just go through all of the items, and which is just if there is a some requirement that I want to display all of these items, or I wanted to just list those items, you have to traverse each and every item. Then only you can get all of those items. Means if the number of items are getting increased, the complexity is going to increase if you wanted to list, right? So that's why we are calling that one as O of n. The complexity is O of n here. The next one is that insertion. Example, if you wanted to insert an item to your array, then what is the complexity, how you are going to do? Example, if you wanted to insert the item at the end of the array, then fine, it is okay. But if you wanted to insert the item in between that, then you have to right shift all of your right side elements, right? So that is where the complexity is there. For the insertion at a given index, means at the last, it is okay. But in if you are trying to insert the item in between, it depends. It might be a O of n log n, right? You are not going to shift all of your items to the right or to the left. It depends. In worst case, it can be O of n, those many movements you have to do. But in average case, it can be n log n. In the deletion, simple thing, if you wanted to delete an item at the last end of the array, it is okay. But if you wanted to delete an item somewhere else in between, or the first item you wanted to delete, then you have to left shift all of your items back. So means the time complexity, worst case time complexity, is going to be O of n. Same thing for the search. If you wanted to search 19 without index, what you can do, you can just simply write a for loop, and you can start searching the item from left to right. If you are trying to search the last item, in this case the item 31 or the element 31, you have to touch each and every item. Means n number of times your step is getting executed, means the time complexity is of n. Same thing for the update. If you wanted to update based upon some index, like if you want to change 19 to some 0, you can immediately do that, because by using index directly, you are pointing to that particular memory location and updating it. So these are the operations what we have on the arrays, and we need to understand these things. Now the second one is linked list. Just a minute. Yeah, the second one is linked list. So it is also another type of data structure. If you wanted to just have connection between one data item to another data item, in such type of cases, you can use the linked list here. So each and everything is going to point to another one, just like a might be you might heard about the blockchains, right? Everything is a chain, one thing to another thing, it is just joined up, and it is just a sequence of items what we have. Everything is connected with the links, and each and in every link, right, what you have, you actually have any data item, and that can have a reference to the another link, I can say, which is also another data item, and it has a reference to the next one. Okay, so here the concepts are called as the link and next link and first one, first or head. These are the terminologies what we are using in the linked list. And what are the types of linked list we have? Are simple, double, and circular. Simple is just forward direction, you can keep on traversing and try to find out whatever you wanted. If you wanted to traverse back some from some place, then you have to use the double linked list. So you can traverse forward, you can traverse backward as well from a given point of a data item. And circular means the head item will be referred in the tail item of the linked list. In that way, these will be joined up. I will just show you the representations how these are going to be. So if you see, this is the single linked list, and if you see here, the first one is the head, and this can be, you say, null. Yeah? And you have a node which is nothing but your link, and that has the data item and a reference of the next item. In this way, if you see the last one, the next link will be null, because it is not connecting or point to anything other. Yeah, in double linked list, if you see, each and every data item is connecting to the next item as well as the previous item. In circular, the last item will connect it to the first item. So this is the way how we can represent the linked list. And the list of operations what we have on the linked list are in this way. So insertion we can perform, means wherever we want we can just insert it. And if you wanted to insert a data item someplace here, then we can just go there and take means point, just get the reference of the next item and put that one in its next, and its reference, add that one to the previous one, then remove the link between these two nodes, so that your item will be inserted over there, and the time complexity is of 1. I'm just checking the time. Oh, sorry, we have only 15 minutes, so I will try to explain a little bit faster way here. The deletion as well, if I wanted to delete a particular item, I can just go ahead and delete that, and the time complexity here is O of 1. For display, if I wanted to just list down all of the items here from head, I have to take from there, I need to traverse one by one and just to get all of those data items, means I am touching each and every item. If the number of items are more, then the time to traverse that entire list will get increased. Same thing for the search. The worst case, if I wanted to get the last item like in the arrays, then I have to traverse from one by one, 1, 2, 3. In that way, I have to keep on going. Yeah. So that is the linked list. I will just go you how to just insert the linked list here. If you say I have the existing linked list here, I wanted to add a new node or the data item. As I mentioned, right, in this node, we should have two things. One is a holder where we can store the data, and another one is just a link or a reference of the next one. So if you see here, what we need to do in the first node, the next is pointing the second node, right? Now, whatever the reference we have in this next node, we need to add that reference in the next. Then we need to refer this new node in the node, like data item dot this data item dot next equal to this data item, and this data item dot next equal to this, so that this link will be automatically removed and my item will be added over there. So these are the steps 1, 2, 3. Now deletion also in the simple way. Yeah, so if I wanted to delete this, I just needs to uh, go to this item, try to find out what is the value stored in this next, and just add that one here. So in this way we can just have the deletion operation here. Okay. Now stacks is also another type of data structure what we have, and stack will be used heavily in expression evolutions. The people who have the .NET background, might be you can know that there are expression trees concept. All of those expression trees are getting evaluated underneath in the .NET framework or the runtime. All are those getting executed through the stacks itself. If you wanted to have any rules engine kind of stuff as well, you have to use the stacks over there to store the final outcome of each and every sub expression of the expression, so that you can perform the operations like and multiplication, whatever you wanted to do. So it is a linear one, and the principle what it follows is that last in first out, because it is just a pile up. First one goes down, next one comes on top of that, in that way, right? So in your expression you can just evaluate one, put that one there, then put an operator, go and next evaluate the next one. While you these all are the values. Now what you can do, you can take the first one out and the operator and the left operand, execute that, you will get the final outcome in that way. So it has push, pop, peek, and full operations in it. Push and pop. Push is nothing but inserting an item to your stack. Pop is nothing but just taking or removing an item there. I will show you how to represent it. If you see here, this is a stack. This is the way how can you keep on pushing there. First data item, second data item. And if you see one side of it, the data structure is closed here. You can't access this, or you can't take the items from here. The only open side is from top. So you have to take one by one out. And what are the operations here? One is push, which is nothing but the insertion. You are only allowed to insert the items on top. Means n number of items you have to insert an item, it will just take one computational unit itself. And pop as well, just taking out the first one. Yeah. If you wanted to just traverse through all of these ones, anyhow, you have to read everyone. Either you need to just keep on doing the pop, 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 pop like that. If the numbers are getting increased, the complexity will get increased. If you wanted to search as well, the worst case, if you wanted to take the last one, the one which you have here, then those many items you have to just pop, means the complexity is O of n. Yeah, same thing for the delete. Now coming to the queues, uh, like the stacks, it is following a principle called as first in first out. uh, it is totally inverse, right? In the stack, whatever the last item is getting inserted, you can take that one out. But in queues, whatever the first item you are putting, you can take that one. And if you see all of the event based mechanisms or the enterprise service bus, these all are implemented based upon the queues data structure. It has NQ, DQ, and peak, full, empty. The representation is in this way. You can just keep on adding. This is a queue. You can just add one item that will go first out. Yeah, and it has two things here. Those one are rear and front. These are the two terminologies what we need to know. Front is nothing but the one from where we can take the items out. Rear is nothing but the place where we can just keep on adding, pushing the new items to that. Queue operations as well. Insertion means which is nothing but the NQ. N number of items you are getting to insert an item, it will just take a time because you are going to just put that item at the rear front. Yeah, at the right front. The DQ, you are taking the item one by one. If you wanted to display all of those items, it is O of n, because the number of items you have is getting increased. Then you have to touch each and every item, means O of n. Searching is also similar thing. Yeah, deletion as well. If you wanted to delete, ideally deletion operation is not performed on the queues, but in case if it is required, the complexity is O of n. Yeah, so these all are the data structures. Now I am getting into the search. As I mentioned, right, we are dealing with the data items. The basic operations what we are doing is search, insert, delete. These are the, and sort. These are the primary things. So if we wanted to search some items from your data set, you need to apply a proper or right search algorithm there. So the search always happens in a sequentially one by one if you wanted to do, hence the complexity is O of n. If you see here, right, if you wanted to search line item 33, then you have to start from the left side. First 10 you have to compare it, and that is not 33, right? In that way you can keep on searching one by one item, you are going to end up with the right item, means the complexity is O of n. If you wanted to search for 44, means you have to touch all of the items. Now, the above one is called as linear search. You are just searching one by one. Yeah. The other one is binary search. Previously, I explained about the divide and conquer principle as part of the algorithms. So, if you see in the above item, right, 33 is at the right side. So, if you divide this one into two parts, then you can avoid searching from 10 to 27. Means you saved 5 computation units there. So that is what binary search is going to do. Means the complexity is O log n. O log n value is lesser than the n. That's why log n is getting used over there. Yeah. And another prerequisite here in the binary search is that all of your items in the data set needs to be sorted. Otherwise, you will end up having the complexity O of n. So if you see how we are going to search here, the item 31 is at the position 5. Now what we can do here is that we can just calculate 9 plus 0 divided by 2. So means we will end up at 4.5, and the value, if you round up that one, you will land at the 27. So you can compare that whether that item is greater than or less than. If in our case it is greater than, so it will avoid searching from 10 to 26, means it will target from 27. It will just go and check from there. So then what it will do, it will again divide the next thing. 5 plus 9 by 2 is 7.5, and 35th item. And here if you see 31 is less than 35, so what it will do, it will take the left side part, and it will try to again divide and conquer here. So it will avoid. Now we have only two items here. Now it will point to the 31, right? And we have only one there, that is 31. So we find out that 31, that's it. In this way the binary search is going to work. And if you see in the binary search as an example, these many iterations as well we are doing here. So to reduce that, there is another search algorithm called as interpolation search, which is just like an enhanced one. So here there is a small formula which needs to be followed, which will just try to find out the closest index of that particular item where the key is also getting considered in this algorithm. In the binary search, the item what you are trying to search, that is not considered while you are trying to break down or divide that entire set.
Venkat, sorry to interrupt. Would you like to answer that question right now? We are 4 minutes into the end of
Yeah,
coming up to the end. So the question is, does time and space complexity also play a major role in deciding which DS to use?
yeah. It is it is based upon the problem what we are trying to address and in which domain area is it. Okay, Based upon that, we have to consider the time complexity. As I mentioned previously, right, the memory is cheaper than the computational power. So it is okay to have small sort of relaxation on the space complexity, but we have to consider the time complexity. Means uh, the algorithms what we need to consider. So like example, as I was explaining about the sorting algorithms or the search algorithms, right? It is not based upon the data structure, it is based upon the operation what you wanted to. The data structure is that how you are going to just uh, encapsulate all of your data and you are going to store. It depends upon the other use cases as well. In some use cases where you wanted to have a traverse through the forward and traverse through the backward kind of stuff to find out it, there you have to use that consider the data structures. So the primary thing here is that what is the right algorithm you are trying to use. Once you decided the data structure needs to be used for your particular use case. Yeah, Manasa.
Yes, Venkat, I think you can go back to the presentation. Sorry.
Yeah, sorry, I thought I can complete it in 1 hour, but not sure. It is taking time. There are a lot of things. Yeah. So if you see in the interpolation, right, it is going to have some sort of formula here. The lower index and the average of the index divided by the actual value difference and multiplied by with the actual searching value and lower value, that will give you the closest index of your item. So if you see in this example, right, if you wanted to try to find out two, if you perform the above equation, you will end up having your pointer at 3. Means you are just skipping all of the items needs to be searched here, right? Means the number of iterations you are performing, that is, those are getting close to 2. Sorry guys, I am just trying to finish it on a speed manner. Hence, I am not getting into the details like the way I explained about the data structures and algorithms. Yeah, bubble sort I explained. We have to take a pair of adjacent elements and start comparing it and start doing the swapping in that way. So as I mentioned, right, the time complexity here is that O of n square. So if you see this set, we have 13, 3, 37, 35, and 30. We need to sort it out. What we will take first, 14 and 13 we can consider. Since 14 is less than 13 is greater than, no need to worry. Now we need to move and take 33 and 27. Since 33 is greater than, we have to swap that one with the 27. Yeah. So in the similar fashion, we have to consider the 27 and the 33. If you see in this way, we have to keep on proceeding further so that we will end up having a sort. So it is O of n square, means the data size is getting increased, then your complexity is getting increased. Now insertion sort. This is another version of the insertion sort. Yeah. So here, if you see, what is going to happen is that you are going to start from the left side to right side, keep on sorting these things. Means you are going to find out the next lowest value and trying to just sort that one in your left side set. In that way, you will keep on going here. And here, same complexity we have. Worst case, if you see 14 here, 14 and 13, yeah, and 14 is the lowest one. So what you will go now, 14 is the lowest one, no need to worry. Now you will try to compare 13 and 27. 27 is the lowest one. Now you will swap those two things. Yeah. And you can compare the next item called 33. Yeah. And if you compare, you can get the 10. Once you get the 10, if you see in the left side list, 27, which is the greater. So now you have to keep on moving left and adjust that 10 before 14. Okay, in this way you can keep on going. This is insertion sort. Now the selection sort. So the selection sort is a little bit enhanced version of your insertion sort here. So what it does is that you can find out the smallest element. In the previous case, within the two sets, right, you are trying to find out which one is less than, and you are going backwards to fit it. Instead of that, here you will first go and find out the lowest one and try to insert that one in the left side. So here also the complexity is going to be same example I am taking here. Instead of just swapping the 14 and 33 here, it will try to go and try to find out the lowest value of the 14 here, 10, and try to take swap that 10 and 14, right, and it will move to the 13 and try to find out the lowest, and it will try to do that. If you see all of this is sequence, it will just doing in that way. This is the selection sort. And merge sort, yeah, as I mentioned previously, it is going to use the divide and conquer. Yeah, it is going to just divide entire set into the subsets and sort that one and start merging it, if you see in this way. Okay, so once you get two consequent elements here, it will sort those ones, uh, and try to 14 33. 14 is the smallest, leave it. Now 33 and 27, right? So in that way it will take that 27 here. In that way it will keep on doing the sorting here. And shell sort. So it uses some formula that is called as Smith formula. What it does is that it creates subsets, and based upon subsets, it will just to do the sorting. Once that is done, then it will apply the insertion sort on the widespread items there. So if you see here, I am using the 4 interval, means uh, if I'm starting from 35th element, 0th element, what is my fourth element here? So I will make these two as a one set, and 33 and 19, these two are another set. 40 through and this one set, in that way. And I will now start comparing these two. Okay, 33 is 35 is greater than, so let's swap. In this, 19 is smaller, let's swap. 27, swap. Here 10 is smallest, no need to swap. So finally I will end up having such type of thing. Just like in illustration, if I take interval as 1, then I will end up having two sets only in this way. 14, 27, 35, 42 is one set, remaining all are in one set, and this is the thing what I am going to have. Okay, and here now I will start having the instruction sort. So if you see, it will keep on just going in this way. And the final one is quicksort. So quicksort is based upon the partition logic, where you are going to select one item as a pivot item, and based upon that item you will arrange all of the items which are less than that pivot item in the left, and the items which are greater than. Okay, you will just segregate those things and bring the selected item into its proper place. Now apply the recursion there, on the left side partition and right side partition, keep going up to the down, so that you can just get the thing sorted. Okay, which is also of n square. Now if you see here, I think this is just like a complexity, time complexity, space complexity, for each and every type of data structure and its operations. As I mentioned, first, based upon your requirement, you are going to select the data structure. After that, you can just implement the right algorithm for its operations, search, insertion, deletion, like that. Yeah, so this is for today. Sorry, guys, I thought to explain in detail, but due to the time constraints, I just took a fast pace here.
I think Venkat, we can do the other one soon as well. Like you said, we can pick up the system design
Yeah, sure.
bit, I think next month. So to anybody who's watching us, we will make sure we cover that bit as well. Thank you so much for being here with us today, Venkat. This was for whoever would have followed and understood this. This was enlightening, I hope, or knowledgeable. There are a few questions. If any of you want to reach out to Venkat offline, as in on LinkedIn, you can always do that. Thank you once again to our audience. Like we told you, we'll be picking this up again for the system design bit next month, maybe whenever Venkat is available, and we'll be arranging for the same setup. So please do join then as well. And thank you once again, Venkat. Thank you for whoever joined us today. See you soon.
Yeah, thank you.